Welcome. Today I will be giving an introduction to Ramsey theory. Consider the following question. What is the smallest number of people needed in a room in order to guarantee that either 3 people know each other or 3 people do not know each other? Eventually, I will encourage you to pause the video and think about this problem on your own. But first, I want to make sure you understand the question. Let me show you why you cannot guarantee this property when you only have exactly 4 people in the room. For the sake of this question, we will say that an edge between 2 people is going to represent the relationship that they have. If the edge is colored blue, then these 2 people will know each other. If the edge is colored red, then they do not know each other. This notation will dramatically simplify our problem. Our goal now is to guarantee that no matter how we color these edges red or blue, we are guaranteed to have a monochromatic triangle. And to show that some number of people does not have this property, all we need to find is exactly one coloring which does not have a monochromatic red or blue triangle. If we color the outside cycle blue and the diagonal edges red, then we'll see that there actually will not contain a monochromatic triangle at all in this complete graph on 4 vertices. This is all we needed to show that we need at least 5 people in order to guarantee this property. And the story on 5 people is honestly not that much different. We can actually use a very similar coloring to avoid monochromatic triangles. Let's let our outside cycle be colored blue and every diagonal edge be colored red. I claim that this coloring does not contain a monochromatic triangle at all. In fact, if you take 2 adjacent blue edges, then the only edge which would complete the triangle is guaranteed to be red. Similarly, if we take any 2 adjacent red edges, then the only edge left to complete the triangle is guaranteed to be blue. Therefore, we found a coloring which does not contain a monochromatic triangle. This shows that we will need at least 6 people in the room in order to guarantee that 3 people know each other or that 3 people don't know each other. And this is where things start to get interesting. I encourage you to pause the video and see if you can find a coloring with 6 different people in our room so that there does not contain a monochromatic triangle. The spoiler is that you are not going to be able to come up with a coloring without a monochromatic triangle in it. And here is how you prove that. Start by focusing your attention on exactly one person. And let's focus on the relationship that this person has with everyone else. Using the pigeonhole principle, we can see that at least 3 of these edges has to be red, or at least 3 of these edges has to be blue. Let's suppose that at least 3 of the edges are red, and we only need exactly 3 edges to be red, so let's just suppose the other 2 are blue. Although, the 3 people who are incident to the red edges must also have some type of relationship. If exactly one of these edges is red, then we're guaranteed to have this triangle right here. So that means none of these edges can be red. We need all of them to be blue. However, if all 3 of these edges are blue, then we necessarily have a blue triangle. This shows that no matter how we color these edges when 6 people are in the room, we are guaranteed to have some monochromatic triangle. And that shows that at least 3 people will know each other or 3 people will not know each other. So that's it. Our answer is 6. Now I know there are some people out there thinking, well, what if we wanted to guarantee that at least 4 people knew each other or 4 people didn't know each other? Well, there is a general concept here that's underlying. This is where Ramsey's theorem comes in. Ramsey's theorem says that for all s and t greater than or equal to 1, there exists an n greater than or equal to 1 such that every 2 coloring of a complete graph on n vertices contains a monochromatic clique of order S or T. You can use this theorem to define a bunch of different numbers. We'll say that the smallest number n, such that every 2 coloring of a complete graph contains a monochromatic clique of order S or T, is denoted R of ST, and these define the Ramsey numbers. The example that we showed earlier says that R33 is exactly equal to 6. A cool thing is that the majority of these Ramsey numbers aren't actually known. I'll put a link below showing which ones are known, but if you find any of the ones that are not known, you can actually get a publication in mathematics. These are by no means easy to find, or else somebody probably would have found them. But in any case, I wish you luck. I hope this video is helpful, and I'll see you next time.